So in this video we're going to discuss hybridization and how to go about knowing when and how to hybridize and draw your orbitals. So there are basically three big points that help us understand hybridization. The first thing is that when we hybridize, we always want to hybridize our bonds and our lone pairs. And don't let bonds trip you up, because one bond in this situation is really an electron group. That's how we're going to define it. And so a single bond, a double bond, or a triple bond are going to be considered a bond or an electron group. Every electron group uses a hybridized orbital, whether it's a lone pair or, like I said, a bond, which is going to be an electron group. So let's use the example of methane. The first thing I did over here, and if you remember from the HONC-X rules, we predict what about carbon when it's in a molecule. That carbon wants 4 bonds and 0 lone pairs. Well, by looking at the electron configuration of carbon, which I have drawn, we see that there is 2 half-filled orbitals, and that we would predict it to have 2 bonds, or possibly 3 if it got an electron from somewhere else. We wouldn't expect it to make 4 bonds. And so the chemists have developed this thing called hybridization to help us understand why or how carbon can and will make 4 bonds, which we see in experiments. So the first thing to notice is that when I'm drawing the 1s, we don't care about it. We only look at the valence electrons. So when we write it down here, hybridize, we don't draw it. So what we do is we say to make 4 bonds, we have to get 4 half-filled orbitals. That is done by saying that this s is going to combine with all 3 of the p's. When we do that, we see that we have 4 sp3 hybridized orbitals, and what that p means is that there's 1 part p, or 1 part s and 3 parts p. So it's mostly p character and a 25% s character. So we have, yes, so I drew this circle to represent that we're going to combine all of these to form 4 separate orbitals that can now produce 4 bonds, 4 individual bonds. So we draw our central carbon atom and we draw 4 tetrahedrally shaped sp3 orbitals. And we know that that hydrogen itself is pretty much only going to have sigma bonds, and it's going to have s orbitals. So the sp3 orbitals that I have drawn here really should be pointing in here. These are the sp3 hybridized orbitals right here, and these are the s orbitals from hydrogen. And so what we see is this tetrahedral type shape, and all of the bonds that we see in this case are sigma. And we will do another example to show how we get some pi bonds going on. Okay, so we have one more example that we're going to show for hybridization, and it's going to illustrate how to use a d orbital when we do hybridization, how to include it. So our example is sulfur tetrachloride, and here's the Lewis structure for it. We have a total number of electrons of 34, and we should see that represented in the Lewis structure, which gives us a lone pair on the sulfur as well as 4 single bonds. What that means is that we've used up we've gone beyond the octet, and when we do that we have to go past the p orbitals when we hybridize. So we include the d orbitals. So we say to ourselves, how many electron groups are coming off of the sulfur? We have a total of 5. So previously we would say, oh, well, if we have 4, then we have to include the S and the 3 Ps. But we have one more that we need. So we have to go into the D's, which we see here. When we do that, we get a sulfur that has an sp3d hybridization, and this should reflect what we see in the Lewis structure. We have a lone pair, which means that one of the orbitals is totally full already, and then we have 4 orbitals, which allows us to form 4 sigma bonds, which is what we have between the chlorines. So then we basically use this information in our Lewis structure to compose a hybridization bonding diagram. And when we do that, we see from the Lewis structure here that we have a seahorse seesaw or a T molecule. And once again, all of these are hybridized. So we have sp3d here, 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 and here. And the chlorines are just sp3 hybridized, so I'm not going to show you the details there. But we can expect to, like I said, those form the sigma bonds. So sigma, 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 and that's just a lone pair occupying that last orbital. And that's how we incorporate D with hybridization. Okay, we're going to continue on with another example. We're going to use carbon dioxide. So the first thing that we can do is write down that we have 16 electrons in our system, because we need to have as many here as we do in our final diagram that we make. If we don't have that number to be the same, we did something wrong somewhere. So it's a good way to check yourself. The second thing that I like to do is draw carbon dioxide's Lewis structure. This will tell us the bonds and where those electrons are, and help us check ourselves when we go to do our hybridization from our electron configuration diagram, which is the next thing that I like to do. So when we draw carbon, we notice that we have 2 electron groups coming off our carbon, so we expect there to be 2 hybridized orbitals. We also expect there to be 2 p orbitals, which are not hybridized because they're forming pi bonds. So we circle the empty with this one, and so that will essentially take one of our electrons and put them in there because they're on the same energy level now, and we have those 2 p orbitals available for pi bonds with our oxygens. Looking at the oxygen itself, we know that lone pairs occupy hybridized orbitals, and we also know that we have 2 of those and 1 sigma bond. So we can say there's how many electron groups on oxygen? There's 1, 2, 3. So we should expect 3 hybridized orbitals from that. But you can also think through it like I just demonstrated, that we know that the lone pairs are going to occupy 1 hybridized orbital each, and that one of these sigma bonds needs to be hybridized and the other one is going to be p. So when we go to form our new hybridized electron configuration diagram, we want to make sure that we pick two of the p orbitals that are going to give us 2 full orbitals, which is where our lone pairs go, and 1 for the sigma bond, and that gives us 1 left over to participate in the pi bond itself. And so this corresponds to what we expect from here, which then we can take this information combined with our Lewis structure to compose our hybridized diagram. So putting carbon in the middle just like we have here, and the oxygens on each end, we can go ahead and start representing this as we see it here. So we've got a sigma bond there, a sigma bond there. We have 2 p orbitals on the carbon. Each one is participating with one of the oxygens, and they have to be parallel on the atom that they bond with. And the way that we say that is that they're parallel or coplanar. They're in the same plane and they're parallel. You notice here, by the way, that I don't really have these bonding. So this is up and that's up. And that's okay. But whenever we actually put our electrons in here and we show that they're occupying the same orbital, molecular orbital, and that's what we have when they combine together as a molecular orbital, they have to be opposite spin. So that's where we take care of it there, as we show the spin is opposite. And we know that that's true from the Pauli exclusion principle. Okay, so that's more or less why that's up and that's down. So we have our two p orbitals coming off of this carbon, one with this oxygen, the other with the other oxygen. We have two sigma bonds coming off of the carbon itself. That's one of the sigma bonds, that's the other. The hybridized orbitals, once again, are where the lone pairs on the oxygens are. So there's two, 1, 2 on that one, 1, 2 on that one. And these are all labeled sp2 on the oxygens. So that's an sp2 as well, sp2, sp2. And once again, if they're in the same plane, then you can actually label these Z and Y, which means that this one could be your Z, your Y, and this one would be your Y. And if this one's your Z there, then the Z p orbital must also be Z. And that is how we do carbon dioxide, or a sp hybridized bound to two sp2 hybridized elements.